Ok, adesso siamo live.
Ok.
Boh, puoi forse cominciare.
Okay, so we can start. So, good afternoon, ladies and gentlemen. It's my pleasure to introduce Marco Scutari from IVSA in Switzerland. He's an expert on statistics, machine learning, and Bayesian networks. Today, he will present us a talk on Bayesian networks and their extensions in modern machine learning.
Thank you all for attending. And yes, that the topic I will talk about today is, as you see on the slides, Bayesian networks. What I want to convey with these 45 minutes I have to convince you about using Bayesian networks is that Bayesian networks have existed for a long time, because you find papers going back as far as the 1980s. But they have seen significant developments in more recent years, let's say after the 2000s and the 2010s, that have brought them up to speed with more modern machine learning models, and their applicability has increased significantly in recent years, whereas it was fairly stagnant in years prior. So I will start giving you an intuition about the definitions and the properties of Bayesian networks as a general model, and then I will try to convince you that the modern extensions to those classic definitions from the last century make them appealing model to apply to complex problems in modern machine learning settings. So let's start from the definition, because everything builds on this. What is a Bayesian network? A Bayesian network is a generative model that you can describe by a combination of a directed acyclic graph. And in that graph, each node in the graph corresponds to a random variable x. And then for each random variable, you have an associated probability distribution, which you use to model the variable in the data. And the graph is useful in the sense that it allows you to take the joint distribution of all the variables that you are analyzing and to decompose it in a set of much smaller distributions that are much simpler to handle from a probabilistic point of view, because they have a much lower dimensionality. This, the idea behind this is that the joint distribution of all the variables, which is the bold X in the notation, it decomposes following the arcs that appear in the graph. So the arcs tell you which variables depend on which other variables, and therefore by the presence of particular patterns of arcs and of paths in the graph, you can find which variables are independent of each other or conditionally independent of each other, given some subset of the remaining variables. And you can use this knowledge to decompose the joint distribution of all the variables you are modeling in the problem you are tackling into one distribution for each of those variables, conditional on the variables that correspond to the nodes that are the parents in the graph of that particular variable. So as you can imagine, if you have a number of arcs that is reasonable, meaning it is a small multiple of the number of nodes, like 2 or 3 times, you can think that the joint distribution of all the variables, so the bold X, it can be very high dimensional, but each of the terms on the right-hand side of the equation at the bottom of the slide will have a dimension that is maybe 2 or 3, because you will have one variable and maybe 2 or 3 parents, which gives a total dimension of about 3 or 4. or 4 dimensions for each of those split distributions. So mathematically, the convenience is that you can take a large problem, a large multivariate problem, and divide and conquer it into a set of smaller problems. Graphically, because it's always useful to see things in pictures, what happens is that you can take a problem with multiple variables, you determine what the dependencies are between the variables, and you represent them as arcs in the graph. And we will get in a second about how you do this. And then after you have done that, instead of having one multivariate distribution, you have, as you see on the right-hand side of this slide, you have one much smaller, meaning lower dimensional distribution for each of the nodes conditional on its parents. So the number of parameters that you actually end up estimating is much smaller than you would think from the dimension of the joint distribution of all the variables. Now, the other advantage is that the structuring the problem as a set of distributions, each one local to a single variable conditional to the parents, makes it possible to choose conditional distributions that are very efficient to estimate and to perform a statistical inference on. And at the same time, it makes it possible to reuse large amounts of results from classical statistical models. So in this spirit, what you find commonly done is that the distribution for each variable conditional to the parent will be some kind of regression model, a discrete. If the variables are discrete, then you will have a logistic regression or a multinomial logistic regression, or maybe an ordinal logistic regression, but it will be some sort of logistic regression kind of model. If the variables are continuous, then the convenient assumption is that you assume that the joint distribution is a multivariate normal, and then each local distribution will end up being a classic least squares, in the simplest case, least squares linear regression model. Or if you have a mixture of variables, some of which are continuous and some are discrete, then you can use a mixture of linear regressions or a mixture of normals interchangeably to get a similar setup. So the second advantage is that you start from a multivariate distribution which is complex to model, and you reduce it to something that is much smaller dimensional, and it boils down to models that have been known and studied in statistics for decades. So properties are known, how to get well-behaved estimates of the parameters of these local distributions of the nodes is known and has been studied again for decades. You have a large choice in how you estimate the parameters of these distributions, because for logistic regressions and for linear regression models, you can pick your choice of frequentist or likelihood-based or Bayesian posterior approach about how you estimate the parameters of each of those distributions. So at the same time, you get to use large amounts of results from statistics, and you get simple models that you can choose how to estimate and how to regularize as you wish, which is that depending on the context you are working with, some choices may be more sensible than others. The third advantage of this construction is that decomposing the multivariate distribution of all the variables into a set of distributions, one for each variable, allows to do programmatically to do what is called exact inference in Bayesian networks, which means to do compute algorithmically any joint or marginal or conditional distribution starting from the Bayesian network without having to go through the joint distribution of all the variables again. So computations that are not feasible, and I mean computationally feasible, not statistically feasible, become feasible because of this decomposition allows you to avoid working with large multivariate distributions and instead working on a collage of much smaller distributions that can be manipulated algorithmically to give you whatever distribution of whatever subset of the variables you are interested in. So this is the definition, and this is why the model is defined in this way. It's convenient in a number of ways to structure the model like this. Now, how do we learn this model? Now, this I will only give you in a very, very high level of detail because there's tons of literature, and it would be a PhD course if I tried to go through like a panoramic of approaches to do that. But the general idea is that according to the definition, once we know what the graph looks like, what arcs appear in the graph, then we can decompose the multivariate distribution efficiently into simple models. So the workflow of learning a Bayesian network from data, it's as follows. You first estimate the structure. So you find out what the graph is by finding out which arcs appear in there. And if you take a Bayesian approach, you do that by trying to find the graph that has the largest marginal likelihood conditional on the data. So you average over all possible parameters that could appear given that graph, and you're trying to find the graph that has the highest marginal probability marginalizing over all possible parameter sets. Once you find this graph, then you take the graph as given, and conditioning on the graph, you do what is called parameter learning, which is given the data and the graph, you estimate the parameters of all the regression models I was mentioning earlier, which is the easy part. Now, it looks like a difficult problem, but it's not as difficult as it would seem at first sight, because the graph you are computing the marginal likelihood of dictates the composition of the posterior and of the marginal likelihood along the same subsets of nodes as the local distributions. So you take the marginal likelihood, for example, that I'm showing you in the last equation. The marginal likelihood of the data given the graph decomposes again into terms that correspond to each node, conditional on its parents. So again, it's not a large multivariate problem that you need to solve, for example, by Markov chain Monte Carlo techniques, because it decomposes, and the parts it decomposes into are simple enough to admit closed form estimates in many situations. About inference, I will not go into this much either. Again, there's more written on the slides that I will tell you aloud. So I gave the slides to Mark, and you are welcome to consult them for more details. The idea about inference is that once you have a model, you have a graph, and then each node has a local distribution, which is some form of regression with parameters that are associated with it. The decomposition of the joint distribution of all variables into a set of small dimensional distributions makes it possible, as I was mentioning, to compute the marginal distribution or the joint distribution or conditional distributions of any subset of variables you may be interested in. The logical consequence of this possibility is that you can do automated inference. So computing the probability of arbitrary events can be done algorithmically, started from the decomposition into local distribution that the Bayesian network gives you. So you only need to specify what computer scientists call the evidence. So what variables you are conditioning on and the values you are conditioning them to take. And the variables of interest, which is the event you want to compute the probability of, or the posterior distribution of. And again, algorithmically, just say what you want to know, and this can be derived algorithmically from a Bayesian network without any sort of computation, either manual computation or Monte Carlo computation. I mean, the solution, the exact solution, can be derived algorithmically in exact form without stochastic simulations or manual computations. Stochastic simulations approach exists because beyond a certain size, when you start having hundreds or thousands of nodes, the exact inference can be pretty slow, and stochastic inference, so performing Markov chain Monte Carlo simulations to compute the posterior in this way, can be faster. But for most problems that we see in practical settings, exact inference is fast enough. So this is the textbook material. Now, as I was saying, that there was the assumptions in order to do this, as we knew them from, let's say, the 90s and the early 2000s, were such that we didn't have much flexibility in what we could do with Bayesian networks, because all the classic results make strong assumptions, and I list the main three, the most important of them in this slide. The first one is that the observations have no missing values, and they are stochastically independent, which rules out any kind of incomplete data or any spatio-temporal kind of data we might want to model. The second one is there are no latent variables, which in practice meant that we could really trust the model only if we had experimental data backed by a suitable experimental design with, blocking, randomization, and like the usual paraphernalia of experimental design. And then we could trust the arcs not to be just artifacts of confounding of various kinds. And last but not least, the literature was very clear. This is a probabilistic generative model. I know that displaying it as a directed acyclic graph in which you have arcs with arrows, it can easily make people, even unconsciously, think that the arrows correspond to the direction of causality. So the head of the arc is the effect and the tail is the cause. But you have no guarantee that the arcs that you see represent causal effects as opposed to probabilistic associations. This was the state of what could be done, let's say, up to 10, 15 years ago. Now, things have moved on, and what I want to concentrate is why Bayesian networks are used more often, like in the last decade, than in the previous three. And the reason is that many of these assumptions have been relaxed in various ways. And I'm going to show you a very quick panoramic of how this has been done, to give you an idea of what kind of applications you can use Bayesian networks for. So the first one I will start from is missing data. So as we all know, analyzing like any kind of real world data are usually incomplete. You have missing data here and there. The theory of missing data dates back to Little and Rubin in like its modern systematic form. So we are talking about the 1980s. It's not anything new. And as a quick reminder, Little and Rubin did this a classification of patterns of missing data that is now classic, which is the missing completely at random, missing at random, and missing not at random situations, where missing completely at random is the easiest to model because the data the values that we see missing in our data are missing just by pure chance. So there is no confounding introduced by the missingness to be short. Missing not at random, it means that is the worst case because the reason why the data are missing cannot be inferred from the data because it depends on the missing values that we are not observed themselves. And so we have no statistically robust way of estimating a model from missing not at random data. We can do things, but we are severely limited in the models we can estimate in this case. So representing a problem with a DAG allows us to reuse this kind of classification from Little and Rubin in the context of Bayesian networks. Because if we take our variables, which are still named x something as in the previous notation, those would be nodes in our Bayesian network, right? Because we want to model them. Then what we can do is we can add other nodes, which are auxiliary variables, which I denote as m here. So there's m1, m2, and so on and so forth, which are binary variables that represent whether for a certain observation, the value of a particular variable, which is the child of the m variable, is observed or not. So we take the Bayesian network classic construction and we incorporate this classification from Rubin about missing data, because that classification from Rubin, from Little and Rubin, will determine which variables m we need to insert in the Bayesian network and which arcs will connect them to the variables that we actually observe. So on the left hand side, you see the missing completely at random, where the missingness doesn't depend on anything else that we actually observe or we don't observe. On the right hand side, you see the missing not at random graphical construction, in which you have missing data that depends, say, the variable m6 that depend on variables that we don't observe in x2, and the fact that those variables are missing will also provoke other values to be missing in a different variable. So this chain of things we don't observe makes it very difficult to reconstruct the model with any kind of reliability. The missing at random situation, which is the graph you have in the middle, still includes nodes that are encode the missingness in the data, but those only depend on variables that we actually observe. So we can try to infer the mechanism of missingness, so the pattern of with which the values are missing from the values that we observe. Now, having done this, we have a Bayesian network again, because all the variables we observe, the missing values that we encode with the nodes m will be 0 and 1 values, and we know the values for each observation for those nodes, because we know whether we observe a value for a particular variable or not for each observation. So all the variables are observed here in some sense. This makes it possible to factorize, like to perform the equivalent factorization to the classic definition of Bayesian network. It just looks more complicated because you have a second set of nodes m, which come with parameters, which are the probabilities of missingness for each variable and each observation. But in the missing completely at random case and in the missing at random case, the decomposition I was showing you earlier still holds. It's just more complicated because it has more terms. It does not hold, however, for missing not at random data. So for the first two of the three cases, we can add auxiliary nodes to a Bayesian network and reuse classic results for the most part. Which means that we can use, again, results from classical statistics to do stuff, because if we fix the graph and we just need to estimate the parameters, we can use the expectation maximization algorithm that works as usual. Like in the classic forms that you find, I don't know, in the books from McLachlan, for example, or from Little and Rubin, how do we estimate a linear regression model in the presence of missing data? So expectation maximization is one option, and it works just as the classic formulation. It just has more than one regression to work on. But apart from that, because like you have one regression for each node here. But apart from that, is just the classic expectation maximization algorithm that you know from the literature. The other thing you can do is you can use Gibbs sampling and estimate the parameter values by posterior. Again, that is the usual Gibbs sampling that you know for generating values from a posterior of a multivariate distribution. Only here, the conditional distributions that you use in each step of the Gibbs sampling are given to you by the Bayesian network, because you have the node conditional on the parents. You don't need to know all the other variables like in the textbook formulation of Gibbs sampling. For generating values for a node, you just need to know its parents. So again, this is a slight variation, but it's still the classic Gibbs sampling. Now, things can get a bit more complicated if you want to estimate the structure of the graph from data, because a full Bayesian approach here is computationally impossible. Because if you work out the math, you don't really need to do that. You just, if you write down the integral as I did it here, and you count the dimensions of that integral, you will see that it's impossible to estimate very well, even with Markov chain Monte Carlo techniques, because it has a dimension that is the product of the number of parameters and the number of missing values that we have in the data, which can grow very quickly for any kind of realistic model. So the recourse from that we have from recent-ish literature is we can recycle the expectation maximization algorithm again to learn the structure, just not in a way that resembles the classic formulation of expectation maximization. The trick is that we change what we do in the expectation step and the maximization step, because in the expectation step, we compute the expected values of the sufficient statistics. And then in the maximization step, we don't estimate the parameters here. But what we do is we use the expected sufficient statistics to compute the marginal likelihood and find the graph that estimates, that has the largest marginal likelihood, averaging over all the possible parameterizations again. Then we iterate in the usual expectation maximization way until we converge, and there are proofs of convergence for this. So this algorithm is proved to converge, the same as the classic expectation maximization algorithm, and we give you a graph. Then conditioning on that graph, then we can estimate the parameters again using the approaches I was showing you in the previous slide. But structured learning is indeed a bit different than it used to be. So there's papers from late 2000s that do all the proofs for that. The advantage is that given the sufficient statistics, the expectations of the sufficient statistics, then we can use standard complete data algorithms for learning the structure of the graph, because the expected sufficient statistics paper over the missing values, and we can essentially ignore them and use the sufficient statistics as if they came from complete data. So it's true that you are slowed down by the EM iterations, but each iteration individually is fast because you can use computationally efficient algorithms for the complete data setting. There's other possibilities, and I will leave you this slide here just for references. You can do variational Bayesian EM if you like, which is in closed form more than the structural EM I just showed you. You can use the BIC in a slightly modified way instead of the marginal likelihood, because that's even faster to compute. You can use distributions that are more tolerant of missing data. There's a few other choices in the literature, which I will not go into. I will leave you the references if you are interested for you to look into. What I want to move to is the other extreme case of missing data, which is a latent variable. So we have a variable for which we observe no values. The first question is, can we reuse what I just said we can do for incomplete data just to handle latent variables as an extreme case of an incomplete data variable for which you observe 0 values? The answer is, if the structure is fixed and we just need to estimate the parameters, the answer is yes. If we don't have a fixed structure and we want to learn the structure of the graph from the data, the answer is no. Because identifying the arcs that connect the latent variables to the observed one is a problem which has huge identifiability issues unless you put restrictions on the structure of the graph that are so strong that you might as well just fix the whole graph structure beforehand and estimate just the parameters. Still, borrowing from other branches of time series and dynamic processes literature, there are things that can be done, because Bayesian networks are general in formulation, and so they can subsume, as particular cases, other models for which there are plenty of results. And I will give you again a quick panoramic of some of these models. The first one is vector autoregressive time series, which are the multivariate extension of classic AR time series. So in an autoregressive time series, you have like a variable observed at time t that is regressed on itself and possibly other variables at time t-1. This condition, this structure of conditional dependence, we can represent as a directed acyclic graph. We just take our variables and we duplicate them across 2 time points, and then we draw arcs from time t-1 to time t. And then we have something that is functionally a Bayesian network. It's dynamic in the sense that each variable appears twice because it appears once for each time point that we are modeling, which is assuming that we have a simple time dependence structure of autoregressive of order 1. But you can do higher orders if you like, but I'm keeping it simple for the sake of notation here. So you can take a vector autoregressive time series and just recast it as a dynamic Bayesian network. And what you get is a much simpler, in a sense, Bayesian network than the general one, because the direction of the arcs is fixed to follow the direction of time. So all arcs go from time t-1 to times t. There is no, you don't need to learn the direction of the arcs between the variables, really. The only exception is if you allow dependencies between variables at the same time points, because then for those arcs, you have to disambiguate the direction because you don't have time telling the direction of the arc for you. It is convenient to do all the usual assumptions for vector autoregressive time series, which I will not go into, like time homogeneity, absence of change points, etc., etc. So all things you know from time series, statistical theory, it is still useful to do here in this setting. But the end result is that you can take models that look like dynamic models. Vector autoregressive are the simplest, which is why I introduced them first. And as you saw in the bottom left graph, you can like replicate nodes and construct what is essentially an infinite dynamic Bayesian network, which can represent in classic form, as you can see, like on the bottom right, DAG, by folding back the nodes at different time points in a single node. But the structure of dependence is what you see in the bottom left. So for each time point, you have all the variables, and they will have parents in the previous time point. Typically, each variable will depend on itself at the same time point, and it may or may not depend on other variables at the previous time point. If you assume time homogeneity, then the pattern of arcs between any pair of two time points will be the same, and the same will be true for the parameters. So you can stack pairs of observations for different consecutive time points to estimate the parameters, same as you do for autoregressive time series. Now, you can also put in latent variables in this idea, and then what you get is a large class of stochastic processes models, the most common of which are hidden Markov models and Kalman filters. So hidden Markov models, as you see in the figure on the top left, you will have like an observed part, which is what is usually shown at the bottom of the diagram of hidden Markov process, and one or more variables that are latent for each time point. And the latent part of the process will determine the dynamics that control the observed part. So it's slightly different than the textbook formulation of a hidden Markov model, but I hope not so much. And you see the similarity between the direct cyclic graph structure and what I was just discussing for autoregressive time series. A Kalman filter, you can build it in a similar way. So just to give you a sketch of the equations for both, the graph for the hidden Markov models, it determines the composition same as the one in the classic definition of Bayesian network, only you have latent node z's among the parents for each observed variable. But then again, estimation is easy because you can reuse all the techniques you know from hidden Markov models in order to estimate the parameters of this dynamic Bayesian network. Similar things I can say for autoregressive time series. If you assume that the residuals are normally distributed in each autoregressive equation, then the joint distribution of the whole vector autoregressive process is a multivariate Gaussian, and then the dynamic Bayesian network formulation you have is a Gaussian Bayesian network in which, again, each node is modeled by a linear regression, same as it would be in a vector autoregressive time series. So again, all the theory you know for autoregressive time series applies for handling these kind of dynamic Bayesian networks. I could say the same for Kalman filters, and I will not go into that either because the literature about Kalman filters covers so much that it would be impossible to cover in any kind of detail. So again, I will show you the key equations that are each latent variable depends on itself on the previous time point and other latent variables at previous time points, and observed variables depend on latent variables at the same time point. So you have this structure in which you can write the x's conditional on other variables that, if you represent them in graphical form, are the parents in the graphs I was showing you earlier. So again, you can use all you know about Kalman filters to estimate these models. Now, having said that 3 or 4 times now, then your question may be, then why should I reformulate all these models and dynamic Bayesian networks when all you are telling me is that they work the same as, you know, various models from more specialized models from the classical literature? The answer is that in the classical literature, you typically assume that the structure of the dependencies is fixed, whereas Bayesian networks give you algorithm to learn the structures of that graph from data, which, you know, can be combined with parameter estimation results from the classical literature to make it work in dynamic Bayesian networks. And reformulating those models as Bayesian networks allows you to use algorithms for performing exact inference on them. So the insights that you can draw from those models are much wider than what the classic literature allows you to do, and it's much easier to get them because, again, the computation of conditional distributions, events, marginal distributions, whatever, is done algorithmically for you. So you just need to have a model, a fixed model, a fitted model from the data, and then you query the model and you ask it, I want to know the probability of this event happening conditional on this evidence I have observed, and algorithmically you will get the answer without having to choose ad hoc model depending on which particular specialized model you are actually using. You can do everything with the same set of algorithms that you have from Bayesian networks theory. The last topic I will go into, because it's time to draw it to a close, is the causality part. So classical Bayesian networks are stated in probabilistic terms. Judea-Pearl changed that in the 90s, and the word caught up at some point in the late 2000s and started saying, okay, we can recycle the theory and the algorithms that we have from Bayesian networks to learn models that are causally accurate. But in order for that to happen, we need to make a few additional assumptions. And Judea-Pearl identified the assumptions that we need to make, which is the three assumptions that I'm showing you here. So the causal Markov assumption, the faithfulness assumption, and the causal sufficiency assumption, what they boil down to is a more general version of what we know from the design of experiment literature, which is we need to ensure that we block any source of bias that we may have from the population because of how we sample it or because of the variables that we don't observe. So faithfulness, the causal sufficiency assumption, and the causal Markov assumption taken together are very similar in what they entail in practice to what we assume for drawing robust experimental designs. We want to do blocking, we want to have randomization, we want to avoid any form of sampling bias that we can adjust for. These and the three assumptions that I'm showing you say the same thing. They're just formulated very differently because the design of experiment theory comes from frequentist classical statistics from the 1950s, and these were devised in computer science in the late 1990s. So you can imagine the language is very different, but in terms of practical application, they say very similar things. For the same reason, these assumptions are very difficult to verify in real-world setting. For the same reason why it's essentially impossible to prove that any sufficiently advanced experimental design is foolproof in terms of, preventing bias and confounding completely, instead of, just giving us a reasonable certainty that it does that. What is the advantage of making these assumptions? The assumptions is that we now, if we say we agree with the fact that these assumptions are satisfied, then the arcs now correspond to cause-effect relationships. And this gives us two very powerful tools to do causal inference, which are, apart from giving us a graphical representation of cause-effect relationships in the form of a DAG, which is nice, it also gives us the ability to target interventions, meaning if we have a system and we want to perturb it in some ways, in order to observe how the distribution of other variables change or does not change, the structure of the graph and the paths that connect different nodes passing through, like other nodes possibly, allows us to identify which variables we should target for interventions in order to see effects in different parts of the graphs that we may be interested in. So if we have variables of interest, which would be, let's say, response variables in regression terms, the DAG allows us to pick which variables to intervene on in order to see if the response variable changes or not. Which, if you think in clinical terms, it gives us targets for treatment, for example. In other applications, it tells us which variables we need control for in order to not affect the response variables, which is what you are more interested in social sciences, for example. The second useful and powerful tool that it gives us is the ability to do counterfactuals. Now, counterfactuals are difficult to explain. The general idea of a counterfactual is that I observe a particular individual and I'm trying to ask what values would variables take for that particular individuals in an alternative universe in which reality is different in some way. So we have at the same time an observations and variables appearing twice in the graph, because we have an individual with variables represented with nodes that we actually observe, and then a duplicate of that connected to other variables that we observe, but corresponding to this alternative reality I'm trying to make inference on in a what-if scenario. I know this is not a crystal clear explanation, because a crystal clear explanation would require a few hours to do. So again, I leave you like a reference for what a counterfactual is that is explained better than I can possibly hope to. And I will show you one example that is very much of interest in the literature, although probably more in economics and social sciences than in the life sciences, which is concerns about fairness. So if you read the machine learning literature, you will see that there are many concerns that when there are machine learning algorithms that make decisions automatically, they may incorporate biases like racial bias, age bias, gender bias that we don't want the model to incorporate and to like perpetuate into predictions, because the data themselves are biased, like the data the models are learned from are biased. Now, counterfactuals allows us to address this because we know which variables are the source of the bias. Again, they would be gender, race, age, like the usual suspects. And then we can remove the bias in predictions by saying, okay, let's say if this person I'm observing here is of a different race than what he or she actually is, or a different gender, of a different age, what prediction would I make? Because if the prediction I would make is different from the prediction I actually make, then I may suspect that I have some sort of bias I don't want to have in the model. Again, this can be represented in graphical forms because, again, we have variables and we are just duplicating some of the nodes in the graph to represent these values in the what-if scenarios those nodes would take. And we can formulate a definition of fairness in the context of a causal network, like a causal Bayesian network, which essentially boils down to the variables that are the source of the bias, like race, gender, etc., should not have paths that connect them to the variables I'm predicting that are not blocked by other predictors. So the values of those variables should not propagate all the way to the variables that I'm trying to predict. The variables of the bias-inducing variables should be blocked by the other predictors I'm using. In practice, you cannot do that completely for the same reason why experimental designs can't guarantee 100% bias prevention. But you can bound the amount of bias that is left in the model to a small amount that is actually tolerable. And even legal formulations of these things allow you to do that. And to conclude, what I've been telling you is I was saying, has graphical form. And this is the simplest possible graphical representation I can give you for that. So if you take a graphical model here, like a causal Bayesian network here, in which I have predictors X and the predicted variable Y, and then I have unobserved confounding and observed confounding. So the observed confounding is the variables A. Now, if you don't condition on the variables X, the value of A can go through X and through U all the way to Y. If you work by Bayes' theorem, what happens? So what we can do is, let's say, I want to find a prediction in like the what if scenario in which I have no bias. So I add this variable Y hat, which is the prediction in the what if scenario in which I have no bias. Then I take the second part of the problem, which is my predictors are affected by the bias. So I want to take my predictors and again split them and duplicate the nodes into two components of predictors, one that depends on the bias variables and one that does not depend on the bias variables you here. And then what I do is I just drop all the part of the graph that is downstream from A. So A, the part of the predictors that depend on A, and the original predictions, which are also affected by the bias through XAU here. And I perform the predictions to make them as unbiased as they can possibly be using just using like the what if scenario variable here, which is downstream from variables that don't have any bias, because you have here the predictors part with no bias and the remaining variables U, which may be latent variables or not, but they are not source of bias in the notation. And in doing so, I keep the structure, the causal structure of the model. So it can be shown that this way of enforcing fairness is causally rigorous and causally consistent. And the model that you get still like has all the nice properties a causal model would have. But again, a general formulation of causality, it can be reduced into graphical forms, and then all the stuff we have been saying about Bayesian networks applies again. How to learn parameters, how to learn the structure, etc., etc. You can reuse them to fill in various parts I haven't been talking about formulating this kind of model. So the conclusion, because I'm slightly late already. Bayesian networks, they're nice because they are graphical generative models that give you nice intuition and automated algorithms to do many things. And they are backed by now 30 years of theory, nearly 40. So there's lots of results are available. At the same time, they subsume lots of models and techniques from classical statistics and computer science, both. So again, many things we don't need to reinvent the wheel to do them. We just draw from things that have been known since time before I was a student myself. At the same time, Bayesian networks give a nice framework for attacking multivariate problems by dividing and conquering them into smaller manageable pieces that are easier to handle, but they still allow you to do many things, including handling latent variables and incomplete data and causality, incorporating all the advances in machine learning that have happened since Bayesian networks were originally developed. So you can have kind of the best of both worlds using modern implementations of Bayesian networks. And this is all from me. So I thank you for your patience, because I'm nearly 10 minutes out of time. So sorry for being late.
Thank you for your very nice and interesting presentation. And now, please make some